Hi students. Now that we have got an understanding of how evolution occurs and how species can arise, now we will look at how populations grow. This is an important aspect of species survival as different species use different techniques to better survive in their ecosystem. In this section, we will learn about growth rates and how population growth can be limited or unlimited. We will also see the survival mechanisms that species take to ensure that their young survive to reproductive age. Our learning objective for this lesson is to understand why species do not always live up to their biotic potential. Consider a single female housefly, which can lay 120 eggs. In 56 days, those eggs become mature adults, and each female, suppose half of them are female, can lay another 120 eggs. At this rate, there can be 7 generations of flies in a year, and that original fly would be the proud grandparent of 5.6 trillion offspring. If this rate of reproduction continued for 10 years, the entire Earth would be covered in several meters of housefly bodies. This unrestrained biological reproduction is called the biotic potential. Luckily, housefly reproduction, as for most organisms, is constrained in a variety of ways. Say, scarcity of resources, competition, predation, disease, or accident. The growth of the housefly population just described is called exponential growth, having no limit and possessing a distinctive shape when graphed over time. A graph of exponential population growth is described as a J-curve of individuals added to a population at the beginning because of its shape. As you can see, the number of exponential growth curve can be rather small, but the numbers begin to increase quickly with a fixed growth rate. For example, when a population has just 100 individuals, a 2% growth rate adds just 2 individuals. For a population of 10,000, that 2% growth rate adds 200 individuals. The exponential growth equation is a very simple model. It's an idealized, simple description of the real world. The same equation is used to calculate growth in your bank account due to compounded interest rates. Achieving the potential of your savings depends on your never making a withdrawal. Just as populations of a species lose individuals and experience reduced biotic potential, not all of your dollars will survive to a ripe old age and contribute fully to your future cash position. A graph of exponential population growth is described as a J-curve because of its shape. As you can see, the number of individuals added to a population at the beginning of an exponential growth curve can be rather small, but within a very short time, the numbers begin to increase quickly because a fixed percentage leads to a much larger increase as the population size grows. In this figure, we see several concepts explained by the various curves in the graph. Note that when there are too many moose, they overshoot the carrying capacity. When this happens, the number of moose is reduced. This is called dieback in this figure. Also note that because the carrying capacity was overshot, it actually reduced the future carrying capacity. The moose affected the carrying capacity by overusing resources. So we'll explore this idea of carrying capacity a bit more. But in this figure, note that the J-curve begins at the bottom left and rises all the way to the top. It falls back, and then another J-curve starts again, it falls back, and another J-curve starts again. In the real world, there are limits to growth. Around 1970, ecologists developed the concept of carrying capacity to mean the number or biomass of animals that can be supported without harvesting any of them in a certain area of habitat. This concept is now used more generally to suggest a limit of sustainability that an environment has in relation to the size of a species or population. Carrying capacity is helpful in understanding the population dynamics of some species, and perhaps even humans. When a population overshoots or exceeds the carrying capacity of its environment, resources become limited and death rates rise. And if you remember the curve we saw in the last slide, once the population growth exceeded the carrying capacity, the population started to fall. Sometimes predator and prey populations oscillate in synchrony with each other. One classic study shown in this figure employed the 200-year-old records of furs sold at Hudson Bay Company trading posts in Canada. The ecologist Charles Elton showed that numbers of Canada lynx fluctuate on about a 10-year cycle that mirrors, slightly out of phase, the population peaks of snowshoe hares. When the hare population is high, the lynx prosper on abundant prey, and they reproduce well and the population grows. Eventually, though, the abundant hares overgraze the vegetation, decreasing their food supplies, and the hare populations shrink. For a while, the lynx benefit because starving hares are easier to catch than healthy ones. But as hares become scarce, so do the lynx. When hares are at their lowest levels, their food supply recovers and the whole cycle starts over again. This predator-prey oscillation is described mathematically as the Lotka-Volterra model, named for the scientists who developed it. So not all biological populations cycle through exponential overshoot and this catastrophic dieback that we saw with our friendly mooses. Many species are regulated by both internal and external factors and come into equilibrium with their environmental resources while maintaining relatively stable population sizes. When resources are unlimited, they may even grow exponentially, but this growth slows as the carrying capacity of the environment is approached. This population dynamic is called logistic growth because of its changes in growth rate over time. The logistic growth curve has a different shape than the exponential growth curve that we saw earlier. The logistic growth curve is a sigmoidal-shaped, or S-curve. As you can see in the figure here, it is the yellow-orange colored line. The exponential growth line is the red line. The S-curve, or sigmoidal-shaped curve, describes a population whose growth rate decreases if its numbers approach or exceed the carrying capacity of the environment. So you can see in this line, as the yellow line approaches the dashed line, which represents the carrying capacity, K, the growth starts to slow down and does not exceed the carrying capacity of the environment. Population growth rates are affected by external and internal factors. External factors are habitat quality, food availability, and interactions with other organisms. As populations grow, food becomes scarcer and competition for resources becomes more intense. With a larger population, there is an increased risk that disease or parasites will spread or that predators will be attracted to the area. Some organisms become physiologically stressed when conditions are crowded, but other internal factors like maturity, body size, and hormonal status may cause them to reduce their reproductive output. Overcrowded mice, for instance more than 1,600 per cubic meter, for instance, average 5.1 babies per litter, while uncrowded mice, less than 34 per cubic meter, produce 6.2 babies per litter. All these factors are density dependent. As population size increases, the effect intensifies. With density independent factors, a population is affected no matter what its size. Drought, an early killing frost, flooding, landslide, or habitat destruction by people all increase mortality rates regardless of the population size. Density independent limits to population are often non-biological, capricious acts of nature, like hurricanes or wildfires. Some organisms, such as dandelions and barnacles, depend on a high rate of reproduction and growth to secure a place in the environment. These organisms are called R-selected species because they are adapted to employ a high reproductive rate to overcome the high mortality of virtually ignored offspring. These species may even overshoot carrying capacity and experience population crashes, but as long as vast quantities of young are produced, a few will survive. Now, other organisms that reproduce more conservatively, for instance, longer generation times, late sexual maturity, having fewer young, these are referred to as K-selected species because they are adapted for slower growth conditions near the carrying capacity of their environment. In this table, we can see the different reproductive strategies that R-selected species have as opposed to K-selected species. So let's just go over this briefly. So an R-selected species, and an example of this might be a cockroach, has a short lifespan, they grow quickly, they come to maturity quickly, they have lots of them, very little parental care, right? So you don't see the mommy cockroach rocking the baby cockroach to sleep at night. And they don't really invest that much effort into their offspring. They're adapted to unstable environments, and they tend to be pioneers or colonizers. They go into places where early in the process. They are generalists, niche generalists, so they can live many, many places. And they tend to be prey, so they tend to be the ones that get caught. And they're regulated mainly by intrinsic factors, and they're very low on the trophic level. So in opposition to this, we have K-selected species. And this might be, a wolf or an elephant, something like that. They tend to have long lives. They grow up more slowly. They tend to have few but larger offspring. And they tend to have a high degree of parental protection and care. So there's an investment that the parents make in the individual offspring. They tend to live in stable environments, and they tend to be arrive later in the stages of succession. They tend to be specialists living in very special environments, and they tend to be predators. And they tend to be regulated by extrinsic factors, and they tend to be high in the trophic level. So these are some of the reproductive strategies that a K-selected species like a mammal would have versus an R-selected species like, say, a cockroach. Idealized survivorship curves include high survival rates for juveniles, that's type 1, uniform mortality risk throughout life, that's type 2, and high mortality for juveniles, with long survival for a few individuals that reach maturity. That's type 3. So these are just different strategies that different species have as they survive. So in this section, we've learned about how populations of species grow. Some growth can be described by exponential growth curves. These are the J-shaped ones. And some can be explained by logistic growth curves. These are the S-shaped ones. We saw how predators and prey can enter into a cyclic relationship where the number of prey strongly affects the population of predators and vice versa. We also learned about the growth strategies that species can use to ensure the continuation of their species. And we learned about survivor curves that describe the life cycles of various species.